Section: Introduction. We're going to delve into the world of neural networks, specifically those that use rectified linear unit (ReLU) activations. These are a cornerstone of modern machine learning. To use these networks for predictions, we first set up an architecture, the layout of the network, then adjust the weights and biases to perform well on known data. We hope that this will then also work well on unseen data. While our ultimate goal is to generalize the network to work on any data, we first need to minimize the risk on our training data. This step is crucial, and understanding its computational complexity is key to advancing the theoretical foundations of deep learning. In this paper, we're going to explore how different factors, like the input dimension and the width of the network, affect the computational complexity of training the network. We're going to focus on two-layer neural networks, which are a standard building block for deeper architectures. A two-layer neural network has a certain number of input neurons, hidden ReLU neurons, and a single output neuron. It computes a map from the input to the output. The weights between the layers and the biases at the hidden neurons are adjusted during training. We also look at neural networks with linear threshold activation. The task of training such a network is to find the weights, biases, and activation functions that minimize the training error for a given loss function. Note that if the number of hidden neurons is greater than or equal to the number of input points, the network can exactly fit any input points, achieving zero training error. Training two-layer ReLU neural networks is known to be a complex problem. The current best algorithm for a convex loss function runs in a time proportional to the number of hidden neurons raised to the power of the input dimension. There are two questions we want to answer. First, is there an algorithm that runs in a time proportional to the number of input points and hidden neurons, raised to a function of the input dimension? Second, is there an algorithm that runs in a time proportional to either the number of input points or hidden neurons, raised to a function of the input dimension? We know that the second running time is possible since the number of hidden neurons is less than the number of input points. However, it remains open whether the first running time is possible. In this paper, we show that the first question can be answered negatively for an input dimension of 2, indicating that we cannot eliminate the exponential dependence on the network size. As for the second question, we further exclude any algorithm running in time proportional to the number of input points raised to a function of the input dimension, even for zero training error. We also obtain similar results if linear threshold activation functions are used instead of ReLUs. On the positive side, we provide an algorithm that runs in time proportional to the square of the number of hidden neurons times the input dimension for ReLU neural networks if the training error is 0 and the function computed by the network is assumed to be convex. This answers the second question positively for this specific case. Section Summary. In this section, the authors discuss the computational complexity of training neural networks with rectified linear unit (ReLU) activations. They focus on two-layer neural networks and investigate how different metaparameters, such as input dimension and network width, affect the complexity of the training problem. The authors also explore the possibility of finding algorithms with polynomial running time based on these parameters, but they conclude that the problem remains nitrogen monophosphide hard and cannot be solved efficiently even with fixed input dimension. Section: Implications and Limitations. Let's discuss the implications and limitations of our findings from different angles. In previous studies, the complexity of training two-layer ReLU neural networks was shown to be nitrogen monophosphide hard for a single hidden layer, but this required a non-constant dimension. When the target error is 0, the problem becomes nitrogen monophosphide hard for every constant greater than or equal to 2, but can be solved in polynomial time for a single hidden layer. Other researchers have provided additional lower bounds for running time and approximation hardness results. The complexity of the problem was also studied in relation to the input dimension. It was found to be W1 hard and had a running time lower bound that increased exponentially with the input dimension for a single hidden layer. In networks where the output neuron is also a ReLU, the problem was proven to be nitrogen monophosphide hard for 2 hidden layers and 0 target error. It was also shown that training two-layer ReLU networks with two output and two input neurons is a complete problem for the existential theory of the reals, meaning it's likely not contained in NP. This implies nitrogen monophosphide hardness, but unlike our results, their method doesn't work for one-dimensional outputs. Training two-layer neural networks can be formulated as a convex program, which allows for a polynomial time algorithm for a constant dimension. However, this requires a large number of hidden neurons, possibly equal to the number of input points, and therefore doesn't contradict our nitrogen monophosphide hardness result for a dimension of 2. Understanding the set of functions that can be precisely represented with a certain network architecture is key to studying the computational complexity of training ReLU networks. This is well understood for two-layer networks, but much more complex for deeper networks. In terms of notation, we define a set of natural numbers, and for a subset of real numbers, we denote the affine hull and the dimension of the affine hull. We also assume a loss function that equals 0 if and only if the input equals the output. We assume a basic understanding of computational complexity theory. Parameterized complexity is a method to analyze the computational complexity of problems. A parameterized problem is fixed parameter tractable if there exists an algorithm that can decide whether a problem instance and a certain parameter value are in the problem in a time that is a function of the parameter value times the size of the problem instance to a constant power. A parameterized problem is polynomial time solvable for every constant parameter value, where the degree of the polynomial doesn't depend on the parameter value. The class XP contains all parameterized problems that can be solved in polynomial time for constant parameter values. It's known that fixed parameter tractable problems are a subset of XP. The class W1 contains parameterized problems that are widely believed not to be fixed parameter tractable. That is, a W1 hard problem is not solvable in a time that is a function of the parameter value times the size of the problem instance to a constant power. It's known that fixed parameter tractable problems are a subset of W1, which is a subset of XP. W1 hardness is defined via parameterized reductions. A parameterized reduction is an algorithm that maps a problem instance and a certain parameter value to another problem instance and parameter value in a time that is a function of the parameter value times the size of the problem instance to a constant power. The new parameter value is less than or equal to a function of the original parameter value, and the problem instance and parameter value are in the problem if and only if the new problem instance and parameter value are in the problem. Section Summary. The implications and limitations of the results in this paper are discussed from various perspectives. Previous work has shown the nitrogen monophosphide hardness of training certain types of neural networks, but with non-constant dimensions. The computational complexity of training ReLU networks is still not well understood, especially for deeper networks. Parameterized complexity theory is used to analyze the computational complexity of problems with varying parameters, and the classes FPT, XP, and W1 are defined to classify the solvability of parameterized problems. Section: Exponential time hypothesis. Let's delve into the exponential time hypothesis, ETH, and its implications. The ETH suggests that a problem known as 3SAT, which involves finding the truth values of Boolean variables, can't be solved in less than exponential time. In other words, there's a constant value greater than 0 that prevents 3SAT from being solved in a time frame that's proportional to the exponential of that constant times the number of Boolean variables. This hypothesis has far-reaching implications, including the idea that certain problems can't be solved in polynomial time, which is a cornerstone of computational complexity theory. The ETH also suggests that finding a clique, or a subset of vertices in a graph where every two vertices are connected, can't be done in a time frame that's proportional to a function of the size of the clique times the number of vertices to the power of a function of the size of the clique. Now, let's talk about the geometry of two-layer ReLU networks. These networks represent a function that's continuous and piecewise linear. Each hidden neuron in the network defines a hyperplane, or a subspace of one dimension less than its ambient space, in a multidimensional space. These hyperplanes form an arrangement, and within each cell of this arrangement, the function is affine, or linear. A hyperplane in this arrangement is defined by a vector that's orthogonal, or at right angles, to it. The difference in the directional derivatives of the function on either side of the hyperplane is equal to the sum of the products of the weights of the neurons and the norms of the vectors, and this value is constant along the hyperplane. If this value is positive, the hyperplane is convex, and if it's negative, it's concave. A point is called a convex or concave breakpoint of the function if it lies exclusively on one convex or concave hyperplane of the function. If we know that the function comes from a two-layer neural network with a certain number of hidden neurons, and we need that many distinct hyperplanes to separate the pieces of the function, then each hyperplane must be induced by exactly one neuron. In the case where the input dimension is 2, each of the hyperplanes in the arrangement is actually a line. We call such a line a breakline and define convex and concave breaklines accordingly. Next, we'll discuss the nitrogen monophosphide hardness for 2 dimensions. We'll prove that training a 2-layer ReLU neural network is a nitrogen monophosphide hard problem for 2 dimensions, which means it's at least as hard as the hardest problems in NP. This rules out any running time of the form proportional to the product of the number of vertices and the size of the clique to the power of a function of the dimension. We'll show that this problem is nitrogen monophosphide hard even for 2 dimensions and a certain parameter equal to 0. We'll do this by reducing it from another nitrogen monophosphide complete problem. Our construction will be such that the function represented by the neural network is equal to 0 everywhere except for a finite set of stripes, in which the function forms a levee, or a ridge. A levee with a certain slope is a continuous, piecewise linear function with 2 convex and 2 concave breaklines. It can be realized with 4 ReLUs. Similar levees have been used to prove the completeness of neural network training, but in a very different way. In their work, levees encode variable values via the slopes of the function on the non-constant regions of the levee. In contrast, in our reduction, we encode discrete choices via rotation of the levees, that is, via the slopes of the breaklines in the 2-dimensional input space. Section summary. The exponential time hypothesis, ETH, states that certain computational problems, like 3SAT and clique, cannot be solved in subexponential time. Understanding the geometry of a function represented by a 2-layer ReLU network is crucial for proving results in this paper. The function is continuous and piecewise linear, with convex and concave hyperplanes that determine its behavior. The paper also proves that 2L ReLU NN train is nitrogen monophosphide hard for 2 dimensions, even when the input is restricted to certain conditions. Section: Selection Gadget. We're going to explain a tool that allows us to simulate a choice between a certain number of options. This tool, which we'll call a selection gadget, is centered at the origin of a plane defined by 2 variables, x1 and x2. We'll use multiple versions of this gadget, each shifted slightly from the original position. The selection gadget is represented visually in a figure. Each of the different choices corresponds to a different slope, with each slope being greater than the last. We start by placing 13 data points on the x2 axis, at the point where x1 equals 0. We'll call this vertical line h0. Next, we need a small positive number, which we'll call epsilon. The value of epsilon will be determined later, but for the gadget to work, it must be less than or equal to the minimum of 2 fractions. 1/3 divided by the absolute value of the first slope, and 1/3 divided by the absolute value of the last slope. With this in mind, we place 9 data points parallel to the x2 axis at the point where x1 equals negative epsilon. We'll call this line h, epsilon. Similarly, we place 9 data points parallel to the x2 axis at the point where x1 equals positive epsilon. We'll call this line h, epsilon. Finally, we place twice the number of options minus 1 data points. For each option, we introduce 2 data points, one on the left and one on the right, with specific coordinates based on the slopes. All these data points are labeled with a y value of 0. It's not too hard to see that a line with a slope corresponding to any of the options fits all the data points of a selection gadget. We won't go into the calculations here, but they're straightforward. More importantly, the selection gadget does indeed simulate a choice between exactly the number of options we started with. If we have a piecewise linear function that fits all the data points of the selection gadget, then that function corresponds to one of the options. To prove this, we first look at the three vertical lines h, epsilon, h0, and h, epsilon. Each of these lines contains a sequence of 9 data points, with the first 3 labeled 0, the next 3 labeled 1, and the final 3 labeled 0 again. For simplicity, let's consider one of these lines and label these 9 data points from P1 to P9. The line h0 actually contains more data points, which will be important later. The function on one of these lines is a one-dimensional, continuous, piecewise linear function with at most 4 breakpoints. Looking at the points P2, P3, and P4, we see that the corresponding y values are 0, 0, and 1, respectively. This can only be the case if there's a convex breakpoint between P2 and P4. Similarly, there must be a concave breakpoint between P3 and P5, another concave breakpoint between P5 and P7, and a convex breakpoint between P6 and P8. This uses up all 4 available breakpoints, so there can't be any other breakpoints. Therefore, the function on the line must be linear outside the segment between P2 and P8. Since P1, P2, P8, and P9 all have a y value of 0, the function must be constant 0 outside this segment. Moreover, there can't be a concave breakpoint outside the segment between P3 and P7, which means the function must be convex outside this segment. However, since P3 and P7 also have a y value of 0, the function must be constant 0 there as well. Now let's look at the segment between P4 and P6. There can't be a convex breakpoint between P4 and P6, so the function must be concave within this segment. Since P4, P5, and P6 all have a y value of 1, the function must be constant 1 between P4 and P6. Putting all this together, we see that the function on the line is constant 0 at first, then increases to constant 1 via a convex and a concave breakpoint between P3 and P4, and then decreases back to constant 0 via a concave and a convex breakpoint between P6 and P7. The exact location of these breakpoints and the slope in the sloped segments isn't determined by the 9 data points we've considered so far. However, when we also consider the 4 other data points on h0, they completely determine the function on this line. The function is 0 if x2 is less than or equal to -2 or greater than or equal to 2, and it's equal to 2 minus x2 if x2 is between 1 and 2. This is the same as when x1 equals 0. Next, we need to consider how the function behaves on either side of h0. To do this, we note that the breakpoints of the function on one of the 3 lines we've considered so far appear as intersections of these lines with only 4 breaklines in total. There are exactly 2 convex breaklines, which intersect h0 at 0, -2, and 0, 2, and 2 concave breaklines, which intersect h0 at 0, -1, and 0, 1. Each of the 4 segments between the lines h, epsilon, h0, and h, epsilon, is intersected by exactly 1 concave and 1 convex breakline. Now let's consider one of the concave breaklines, which goes through 0, -1. This line can't intersect the second segment, because if it did, it would intersect h, epsilon, at a point where x2 is less than -8/3, and it wouldn't intersect the third or fourth segments. This is a contradiction, because there are only 2 concave breaklines and both the third and fourth segments must be intersected by exactly one of them. Therefore, this breakline must intersect the first segment instead. By similar reasoning, we can conclude that the first 2 breaklines intersect the first and third segments, and the last 2 breaklines intersect the second and fourth segments. Combining this with the fact that the function on each of the three vertical lines has an increasing section from 0 to 1 and a decreasing section from 1 to 0, we can conclude that the four break lines don't cross between h, epsilon, and h, epsilon. If we focus on the quadrilateral enclosed by the first two break lines and the lines h, epsilon, and h, epsilon, we can see that the function is constant 0 on the first break line, constant 1 on the second break line, and linear within the quadrilateral. Since the lines h, epsilon, and h, epsilon, are parallel, the corresponding two sides of the quadrilateral must have the same length, which means the quadrilateral must be a parallelogram. In particular, the first two break lines must be parallel. Similarly, the last two break lines must be parallel. Let's call the slope of the first two break lines s and the slope of the last two break lines t. To complete the proof, we need to show that all four break lines are parallel, which means s equals t, and that this slope value is equal to one of the slopes we started with. Without loss of generality, we can assume that s is less than or equal to t. If it's not, we can just mirror the gadget along the x2 axis. We can see that s is greater than or equal to the first slope and less than or equal to the last slope, because both of the first two break lines intersect the third segment, and both of the last two break lines intersect the fourth segment. Let's define I as the maximum value of I such that the ith slope is less than or equal to s. If I asterisk equals the number of options, then s equals t equals the last slope, and we're done. Otherwise, consider the data point on the right corresponding to the I asterisk th option, which has a y value of 0. If we look at what the function looks like on the vertical line through this data point, we can see that the four break lines intersect this line in exactly the order we've defined, from bottom to top. This means that these lines don't cross between the x2 axis and this line. By our previous conclusions, this implies that the function is 0 outside the intersection points with the first and last break lines, increases from 0 to 1 between the first two break lines, stays constant 1 between the second and third break lines, and decreases back to 0 between the third and fourth break lines. By our choice of I asterisk, we know that the I plus 1 th slope is greater than s. If we calculate the x2 coordinate where the first break line intersects the vertical line, we find that it's less than the y coordinate of the data point. Since the data point has a y value of 0, this means that the data point doesn't lie below the last break line. Looking at the intersection point of the last break line with the vertical line, we can see that the slope of the last break line is less than or equal to the I plus 1 th slope. Therefore, we have s less than or equal to t less than or equal to the I plus 1 th slope, which implies that s equals t equals the I asterisk th slope. This means that all four break lines are parallel and have one of the slopes we started with. Therefore, the function is the line with slope equal to the I asterisk th slope, which completes the proof of the lemma. Section summary. The selection gadget is a model that represents a discrete choice between multiple possibilities. It consists of different slopes and data points placed on the x_1, x_2 plane. By analyzing the behavior of a continuous piecewise linear function that fits the data points, it is shown that the selection gadget accurately models the discrete choice between the given possibilities. Section. Combining multiple selection gadgets. We've already discussed how to construct a single selection gadget. Now, let's talk about how to use multiple selection gadgets at the same time. We can think of this as stacking multiple selection gadgets on top of each other along the x2 axis. To formalize this, we define a selection gadget with an offset z. This is just like the selection gadget we've already discussed, but we add z to all the x2 coordinates. This means the gadget is centered around the point 0, z. Now, let's consider a set of data points that come from m selection gadgets. Each of these gadgets has an offset, which we'll call z1, z2, and so on up to zm. Each gadget also offers a choice between a certain number of slopes, which we'll denote as s_i_j, where I is within the range of the number of slopes for each gadget, and j is within the range of the number of gadgets. We also need to choose a small value, which we'll call epsilon. This value is the smallest of two fractions, 1 divided by 3 times the absolute value of the first slope of each gadget, and 1 divided by 3 times the absolute value of the last slope of each gadget. We choose this value so that 3 vertical lines, with x1 coordinates of epsilon, 0, and epsilon, each contain either 9 or 13 data points from each gadget. We also define delta as the smallest difference between two consecutive slopes in the m gadgets. And we define s as the largest absolute value of all the slopes. With these definitions in place, we can state a lemma. If the distance between the offsets of two consecutive gadgets is large enough, then fitting all these data points is equivalent to independently choosing one slope for each gadget and adding up the corresponding levies. To be more precise, if the difference between the offsets of two consecutive gadgets is at least 8s delta plus 6, then there are exactly the product of the number of slopes for each gadget, many continuous piecewise linear functions mapping from r squared to r with at most 4 meters breaklines fitting the data points of the m selection gadgets. The proof of this lemma involves showing that each of these functions fits all the data points, and that all functions fitting the data points of the m selection gadgets are of the claimed form. This is done by induction on m, with the base case m equals 1 given by the lemma for a single selection gadget. The proof also involves considering 3 vertical lines with x1 coordinates of epsilon, 0, and epsilon, and showing that the function restricted to each of these lines is a one-dimensional continuous piecewise linear function with at most 4 meters breakpoints. The proof concludes by showing that subtracting one of the levies from the function eliminates 4 of the 4 meters breaklines, and applying induction to the resulting function and the remaining selection gadgets completes the proof. Section Summary. The section discusses the process of combining multiple selection gadgets. These gadgets are stacked along the x_2 axis and each has an offset z. By choosing appropriate offsets and slopes, it is possible to fit all the data points of the gadgets by independently selecting one slope for each gadget and adding up the corresponding levies. The proof shows that if the distance between the gadgets is large enough, there are exactly prod_j equals 1, m, l_j many continuous piecewise linear functions that fit the data points of the gadgets. Section. Global construction. We're now prepared to explain our comprehensive reduction process. Given a formula f, which is a conjunction of clauses C1, C2, Cm, with variables v1, v2, vn, we create data points in a three-dimensional space, r² xr, that can be perfectly fitted with 4 times the sum of m and n ReLUs. This is possible if and only if f is a yes instance of points. Our construction will include selection gadgets for each clause and variable, and additional data points to ensure consistency. We'll use a small difference value, delta, which is 1 divided by twice the number of clauses. This will be the smallest difference between any two consecutive slopes in any selection gadget we use. Also, no slope will be greater than 1 in absolute value. To apply our lemma at the end, we need to maintain a distance of at least 16 meters plus 6 between the centers of the gadgets. We'll start by describing the positions and slopes of the selection gadgets. For each clause Cj, we introduce one selection gadget with offset j times delta and 3 different slopes. These slopes are all between -1 and 0. The choice of slope for the JTH selection gadget corresponds to choosing the RTH literal of the JTH clause as the one that is set to true. For each variable v, we introduce one selection gadget with offset I times delta and 2 slopes, -1 and 1. Choosing the levy with slope -1 corresponds to setting the variable to true, while choosing the levy with slope 1 corresponds to setting the variable to false. If the RTH literal of clause Cj is v, then we introduce a data point at the intersection of the center line of the levy with slope corresponding to the selection gadget for Cj and the center line of the levy with slope 1 corresponding to the selection gadget of v. We then prove a useful lemma. For each j and r, there are exactly 2 out of the possible levies defined by the selection gadgets which are non-zero at the point p_j, r, where v is the RTH literal in Cj. Finally, we are ready to prove the main theorem. We reduce from points and construct an instance of 2L ReLU NN train with k equal to 4 times the sum of m and n and gamma equal to 0 as described above. We introduce points with rational coordinates which are polynomial time computable. To prove equivalence between the points instance and the constructed instance, we first assume that the points instance is a yes instance. We claim that the following function, which is a sum of m plus n levies and thus realizable with k ReLUs, exactly fits all the constructed data points. Now suppose conversely that the constructed data points can be precisely fitted with a function f representable with k ReLUs. We claim that setting v to true for I in t and v to false for I not in t sets exactly one literal per clause to true. This completes the overall proof. Section Summary. In this section, the authors describe the construction of data points in 2D space that can be fitted with ReLUs to determine the satisfiability of a given logical formula. The construction involves selection gadgets for each clause and variable, as well as additional data points to ensure consistency. The authors prove that the constructed data points can be fitted with ReLUs if and only if the logical formula is a yes instance of the problem. Section W1. Hardness for 4 ReLUs. We're going to discuss the complexity of a problem involving 4 rectified linear units, ReLUs, a type of function used in neural networks. We'll demonstrate that this problem is unlikely to be solved efficiently, even when we're aiming for 0 error. In fact, we'll show that the time it takes to solve this problem increases exponentially with the dimensionality of the input data, based on the exponential time hypothesis, ETH, a conjecture about the difficulty of certain computational problems. We're focusing on a specific problem, which we'll call 2L ReLU NN train, with 4 ReLUs and 0 target error. We'll show that this problem is W1, hard, a term used in computational complexity theory to describe problems that are unlikely to be solved efficiently, with respect to the dimensionality of the input data. We'll also show that it can't be solved in a certain amount of time, which we'll denote as rho d n to the power of little o of d times a polynomial function of L, where L is the length of the input data, for any function rho, assuming the ETH. We'll prove this by reducing the problem to another problem, known as the 2hyperplane separability problem. This problem involves determining whether 2 hyperplanes can strictly separate 2 sets of points. Q and P. A hyperplane strictly separates Q and P if, for every pair of points, one from Q and one from P, the line segment connecting the 2 points is intersected by at least one hyperplane, and no point from either Q or P is contained in any of the 2 hyperplanes. We'll show that the 2hyperplane separability problem is also W1, hard with respect to the dimensionality of the input data and can't be solved in a certain amount of time, which we'll denote as rho d m to the power of little o of d times a polynomial function of L, where m is the total number of points in Q and P and L is the size of the instance, assuming the ETH. We'll also show that if there is a solution to the 2hyperplane separability problem, then there is a solution where all the points in Q lie entirely in one region of the hyperplane arrangement and the points in P lie only in the 2 neighboring regions. Furthermore, we'll show that the hyperplanes can be assumed to have a certain minimum distance, which we'll denote as epsilon, to each input point. We'll then construct an instance of the 2L ReLU NN train problem, where the input data consists of certain points derived from the points in Q and P, and show that if there is a solution to the 2hyperplane separability problem, then there is a solution to the 2L ReLU NN train problem. Conversely, if the points in the 2L ReLU NN train problem can be exactly fitted by a function realized by 4 ReLUs, then there is a solution to the 2hyperplane separability problem. Finally, we'll note that if there was an algorithm that could solve the 2L ReLU NN train problem in a certain amount of time, which we'll denote as rho d n to the power of little o of d times a polynomial function of L, then this would imply an algorithm that could solve the 2hyperplane separability problem in a certain amount of time, which we'll denote as rho d m to the power of little o of d times a polynomial function of L, contradicting the ETH. Section Summary. The section discusses the hardness of solving the 2L ReLU NN train problem with 4 ReLUs and 0 target error. The authors prove a lower bound of n omega d running time based on the ETH, showing that the problem is W1 hard with respect to d and not solvable in rho d n o d poly L time. They provide a parameterized reduction from the 2HYPERPLANE separability problem, where two hyperplanes strictly separate two sets of points, and show that if there is a solution, then there is a solution where one set of points lies entirely in one region of the hyperplane arrangement and the other set of points lies only in the two neighboring regions. Section. Hardness results for linear threshold activations. Let's delve into the complexity of training neural networks with linear threshold activation functions, which are less commonly used today but have a rich history. These functions map any input to 1 if it's greater than 0, and to 0 otherwise. When we train these networks, we can't assume that the weights are either -1 or 1, as we do with ReLU networks. This is because the normalization technique we use in the ReLU case doesn't apply here. The key to understanding the complexity of training these networks lies in their geometry. Each function represented by a two-layer linear threshold network is piecewise constant, with the pieces defined by the arrangement of hyperplanes corresponding to the hidden neurons. Our previous reductions for the ReLU case used two ReLUs to approximate step functions from 0 to 1 and from 1 to 0. We can easily adapt these reductions to the linear threshold case. We find that training a two-layer linear threshold network is nitrogen monophosphide hard even when the dimension is 2 and the target error is 0. This is proven by using a similar reduction to the proof of a theorem for the ReLU case. Instead of a sum of levies, we use a sum of stripes, where the function attains value 1. This allows us to build selection gadgets and a similar global construction. The number of required linear threshold neurons is only twice the sum of the number of clauses and variables in a Poit's instance. This is because each stripe can be realized with 2 linear threshold neurons, compared to the 4 ReLUs required to build a levy. We also note that the W1 hardness result extends to linear threshold functions. This is proven by considering the LP loss, which counts the non-zero components of the difference between the predicted and actual outputs. For each value of P, training a two-layer linear threshold network with one hidden neuron is nitrogen monophosphide hard, W1, hard with respect to the dimension, and not solvable in polynomial time for any function assuming the exponential time hypothesis, ETH. Finally, we find that training a two-layer linear threshold network with 2 hidden neurons and a target error of 0 is W1. Hard with respect to the dimension and not solvable in polynomial time for any function assuming the ETH. This proof is simpler than the one for the ReLU case. Instead of 2 ReLUs to realize a step of height 1, we can simply use one linear threshold neuron. Now, let's contrast these hardness results with a tractable special case where all coefficients are 1. In this case, the neural network realizes a convex continuous piecewise linear function with at most 2k distinct pieces. We show that this case, which we call 2L ReLU NN train L plus, with a target error of 0 is fixed parameter tractable for the parameter d plus k. We can solve this problem in exponential time in terms of k and polynomial time in terms of the input bit length for a target error of 0. We use a search tree algorithm to check whether the data can be exactly fitted with k-convex ReLUs. We define 2k sets where each set corresponds to a certain subset of active ReLUs. For given point sets, our algorithm checks whether the points can be exactly fitted by k ReLUs with the additional constraint that each set is a subset of the piece corresponding to its active ReLUs. The correctness of our algorithm follows by induction on the number of points. Each call to the algorithm takes exponential time in terms of k and polynomial time in terms of the input bit length and recursively branches into 2k options. The depth of the recursion tree is bounded by the dimension of the feasible polyhedron, which decreases with each recursive call. This results in an overall running time of exponential time in terms of k squared d and polynomial time in terms of the input bit length. This result also holds for the concave case where all coefficients are -1. However, if positive and negative coefficients are allowed, our search tree approach does not work since we cannot check for forced points anymore, which is necessary to ensure a bounded recursion depth. It is unclear whether this issue can be resolved for 2 or 3 hidden neurons.